Hello everyone, here we'll be talking about chapter 4.7, which is a discussion of optimization problems. Now what an optimization problem really is a problem where you're given a situation and asked to find either the largest such parameter or smallest such parameter, depending on the question. So optimize really means find maximum or minimum of a particular scenario. Okay, so here I just talk about the process really that I would like for you to follow, which basically is the only really way of doing it. And the first step is to label and assign variables and figure out exactly what is being optimized and assigning appropriate value, variables for those basically. And the second step here is definitely the hardest step, so let me write that in red. This is usually the hardest step here. This is where people are going to struggle. And here we want to find or construct a function for the given parameter to be optimized in terms of only one variable if possible. Sometimes you can only get in terms of maybe two variables, but then you may have another equation relating those two somehow. When that's the case, you have to be careful because chain rule comes into play and you get weird things happening. So it's possible, but it's just best to write it all in terms of one variable so you don't have to worry about weird things like chain rule or product rule kind of coming up sneakily, basically. Third step is to find the max and min, depending on the question, of the function. So if it asks you to find the largest such as something, find the maximum. And if it's asking you to find the lowest such something or the smallest, like minimize cost or something like that, then you want to find the minimum of the function. Now let me say here that of course in order to find max or mins, we look to see where the derivative is either 0 or undefined. Those are the possible candidates, possible x values, where we have a max or min is if the derivative is 0 or undefined. But let me just say that for the problems we'll be seeing, basically this is all you do. And in fact, usually, just because of the nature of how things work, if you are to find a function that satisfies whatever parameter we're talking about, let's say area or like I said earlier, cost or something like that, the chances are it will only have a max or a min, and you'll be able to kind of see that there's really no other way to answer the question. So again, we'll see that as we go along, that there's not really too much guesswork here basically. And step 4 is to finally interpret or answer. Sometimes they may want different things, it just kind of depends on the wording. Okay, and also remember here to include units that may be helpful. So here, for this example, it's a pretty standard problem to introducing this material. A farmer has 2,400 feet of fencing to fence off a rectangular field bordering a river. No fence on the riverside is required, and we want to know what are the dimensions of the largest such field. Now, of course, getting a picture going never really hurts, so I'm going to try to do that the best I can. So basically we have a river, and then we have a rectangular area like this. We want to maximize the area of this rectangle. Now, what's the area of a rectangle? Area of a rectangle is length times width or base times height. I'll just call it length times width. Now, so we're kind of jumping to step 2 here, really. But notice what we're trying to what we're trying to optimize is the area. We want to maximize the area. Find the dimensions with the largest such area. Okay, so we want to find an equation for A. In fact, we want to find a function for A. So I want to write A in terms of some variable. Here, A is in terms of 2 variables. So we want to write it in terms of 1 variable. Now, the only thing is there's something I haven't used here, and that's the fact that we have 2,400 feet of fencing. And that's something I didn't say in the wording here, but we're to use all the fencing in this case. So with that being said, then if this is the width, and this is the length, let's say, then what must be true is that the perimeter here, the length plus the width plus this width, notice we're not bordering this side, so there's no fence on that river side. I'll just draw waves there so we understand it's a river, I guess. Yeah, so W plus L plus W must add up to 2,400. So if that's the case, then what we actually get as a consequence of this is that, well, L plus 2W equals 2,400. So if you want, you can actually solve for L in terms of W. So L is just 2,400 minus 2W. And this totally works because now we can plug this into our equation here. So L is replaced with 2,400 minus 2W just like that. So now we can say that A in this case is a function of W only. So we've done step 2 here. We've written the function in terms of only one variable. Now the next step is to find the max or min of this. Now this function, you'll have to distribute the W to kind of see exactly what I'm talking about. But it's 2400W minus 2W squared. And that is actually a facing down parabola that only has a maximum. And of course, since this represents area, we want to find the largest such area, so that makes sense. So like I said, usually it's always going to be the case that this guy works. And it does in this case. And I said f prime, but it depends whatever you call the function. But here we're calling it a, and it's not of x, but it's of w. So now we're going to find the max and min by max or min by taking this derivative and setting it equal to 0. And notice its derivative, of course, is going to be 2400 minus 4w. And that's never defined, never undefined. So we'll set it equal to 0, of course, like this says, one or the other. And adding 4w to the other side and dividing by 4 gives us the w is equal to 600. Okay, good. So now we've actually found out that w must be 600 feet. So this is also 600 feet, so these are equal. But now what's L? Well, L is 2400 minus 2 times 600. So since we know w now is 600, we can plug it in, and we actually get that it's 2400 minus 1200, which is 1200 feet itself. So now it could have asked us to find the largest such area, where we just multiply them and get the area, and write that as the answer in the correct units. But here they're not asking us for the largest such area, they're asking us for the dimensions of the largest such area. So this is where the interpretation comes into play. So our actual answer here is that it's a 600 by 1200 rectangle. 600 feet by 1200 feet rectangle. And that's the answer for this problem. So I didn't quite label the steps here. Let me see, maybe we can kind of try to do it. So really here, this is us getting an idea of things as far as labeling. So that's step 1 kind of. So a picture doesn't really hurt here. Step 2 was us creating the function, which is all of this. Step 3 was us finding the max and min. And then that was this guy. That's where the max occurs. I should, max or min is what I meant to say. And then step 4 is us interpreting the answer. Fantastic. So this is, again, is a pretty good example. It wasn't super complicated though. Now we're going to look at one that's a little harder, not super complicated, but still just a little harder. So let's take a look at that right now, and then we'll see how far it goes as far as how many examples we'll actually do, based, again, all on this one idea here. All right, so in this example, we're asked to, well, find dimensions of the can that will minimize cost where the can has a given volume. So here it says a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions of the can that will minimize the cost of metal to manufacture the can. Now this problem's a little funny because we actually have the wrong unit here. So normally for volume you want things in, I don't know, inches cubed or feet cubed or something like that. And as it turns out, 1 liter, I believe, 1 liter is 1,000 centimeters cubed. And that better be the case, because that I think would kind of help a lot. Because if that was the case, then we can just cube root it and get 10 centimeters. So let me investigate that real quick. Okay, so I just wanted to check to be sure, and it is indeed the case. But by the way, you won't be required to remember these weird conversions if they're not super obvious ones, and this one I don't feel is super obvious. But maybe, you know, it depends. Maybe you saw this and you thought, oh yeah, that is obvious. Who knows? But to me, it's not. So now, of course, this is volume. So we're trying to what? We're trying to minimize the cost of the metal of the can. So let me just draw an image to figure out what's going on. Maybe the drawing the image will help. Who knows? So this is the can we want to manufacture, let's say. We want to minimize the cost of the metal. We're not giving any other information besides the volume of the can. So we know how much material we want it to hold. But if we're manufacturing the can, assuming that it's all made from the same metal and it costs the same amount per, well, I mean, I guess it would be per pound, or, I mean, if you think about it, if you're buying metal as a manufacturer, you would buy it per dimension or per area, basically. So what we want to do really here is minimize the surface area of this can. I guess you could buy metal by pound maybe, but it's really by surface area, because the weight of a sheet would be evenly distributed amongst its area, so hence you would buy it by the area, which sounds a little funny, but that's how it is actually. So what we want to do now is we want to kind of split this up into these two-dimensional pieces so we can essentially stamp the pieces out of a sheet to construct this. That's kind of the idea there. And in fact, if you split this up, what you'll have to do is you'll notice that you'll have two circles, one for top and one for bottom, so I'll write them in that location, or draw them in that location. And if you make an incision here, vertical incision along the can, along the wall of the can, you'll actually see that this piece unravels kind of like this, and it's just a rectangular sheet actually, which makes a lot of sense. Now, if we call each of these circles to have the same radius r, of course it's a cylinder, so they have to have the same radius. Then, well, I guess this, by the way, would have to have a height, so we can call this height h. So I'm just using kind of standard labelings on this shape, kind of like how we saw with the previous problem, area was length times width. Those are standard labelings. So, but now what we notice is that we're left with this rectangle that's an h by something. And in fact, what this something is, what this length is really, if you think about it, is just the circumference of the circle. Because if you construct it back, this is going to wrap around so that this side gets glued exactly to this side here. And they meet. So that means that it wraps around the circle, so the length here is the circumference of the circle, which is 2 pi r. Fantastic. And in fact, really what we've discovered is that the surface area can be found as the sum of the areas of these two circles, which is pi r squared each, so we have two of those, plus the area of this rectangle, which is 2 pi r times h. Awesome. But now the issue is that we have two variables here. We want to minimize surface area, so we're going to call this maybe s. I'll use s. So I'm going to call it s of something. But I want it to be in terms of only one variable, not two. So there must be a way we can relate r and h. And now here in this setup, in this formulation, there's only one thing we haven't used from the problem, and that was the given information that we have this volume. So we can say that the volume is equal to 100 centimeters cubed. And similar to how we did for surface area, we can find a volume formula for the volume of a cylinder. And that's something you should kind of know. So for a cylinder, it's just literally the area of the circle, which is pi r squared, times the height. So this is just pi r squared h. Great. And what we know now is that the volume is equal to 1,000. So let me write that here. I wrote centimeters cubed here just to remind us. So with that being said, surface area will be in centimeters squared as far as the unit goes. But now look, now we can write h in terms of r by just dividing. So that h is 1,000 over pi r squared. So again, this is the hardest part, finding the function in terms of one variable. So now we've written s in terms of r, or at least we will. So this is 2 pi r squared plus, so it's going to be 2 pi r times 100 over pi r squared. Or 1,000 over pi r squared is what I meant to say. So there's a little bit of cancellation and combination for the last term here. So 2 times 1,000 is 2,000. One of the r's cancels and the pi's cancel completely. So really we get 10,000 over r, or 2,000 over r. Perfect. So there we go. This is s of r, and now we're ready to find the max or min by, well, finding its derivative and setting it equal to 0 or undefined. So now let me do that here. So s prime of r is 4 pi r by power rule. And really we can write this actually as 2,000 r to the negative 1 would have been the better way to write it for derivative. So that this derivative is negative 2,000 r to the negative 2. And if you were to write this as one fraction, it of course would all be over r squared. So I'll do that just to show you. So this is 4 pi r minus 2,000 over r squared. And then if you write this as over 1 and multiply top and bottom by r squared. There's another way of doing it as well, but this is probably the best way to see it maybe. The other way to do it would be to just set this equal to 0 and factor out the smallest power of r, kind of like we saw in 4.5 when we were sketching graphs. So here we end up getting is 4 pi r cubed minus 2,000 all over r squared. So this is either 0 when the top is 0 or undefined when the bottom is 0. Now, when the bottom 0 and it's undefined, the radius is equal to 0 because r squared would be 0. And if the radius is equal to 0, you have a 0 radius, so you don't have a can. Which technically is a correct answer because a 0 by 0 can would minimize the area actually. That's the smallest such area, surface area. But then we have no can and we have no problem. So it's kind of weak. It's something you don't want to do. So instead, we're going to set the top equal to 0. So setting the bottom equal to 0 just gives us r equals 0, which is not really good. It's an answer, but it's not one you want. And here, if you just, add 2,000 to the other side, you get 4 pi r cubed is equal to 2,000. Dividing by 4 gives us that pi r cubed is equal to 500. So that means, solving completely, we get that r is equal to 500 over pi, all to the 1/3 power, or let me just write it as the cube root of that. Perfect. So this is where we have our minimum. And in fact, I know it's a minimum just because it can't be anything else. Again, because of the nature of this kind of setup. But to actually find out that it's a minimum, you could find the second, so remember here we have a true horizontal tangent line because this came from the top of the derivative, or numerator of the derivative being 0. So you can actually find the second derivative to apply the second derivative test, and you'll see that it'll only be negative. And in fact, it's not hard to do that, but derivative here will be 4 pi, and then derivative of this will be, it'll be positive 4,000 to the negative 3. So it seems like that's going to be, then we have to plug this in to see if it would be positive or negative there. And it should be concave, no, sorry, it should be concave up there. There we go. So I misspoke. The second derivative should be positive in order for this to be a minimum. And again, you can see that when you find the derivative, you just get 4 pi, which is positive, and here by power rule, that becomes a positive, 4,000 r to the negative 3. So it doesn't take too much work to show that this is indeed a minimum, actually. That's good. So that's really it, but now we want to find the dimensions. We only found the radius, and now to find the height, we'll just plug it back in, so we'll have a radius by height. If you want to find diameter by height, then just double the radius to get the diameter. But let's see if we can plug this back in to find the height now. And we have the height formula right next to it, so let's see if we just plug this in. Let me do this. So it's 1,000 over pi, and I'll write times r to the negative 2, which is the reciprocal of r squared. Now, I'm writing that because since this version of r, the way it's written, it's a fraction, it's best to multiply by its reciprocal when dividing by it. So we're going to actually multiply by the reciprocal of this, but we want to square it as well. So let me just write it reciprocated twice. Maybe that kind of helps. Why would I want to do that? Because if you, there are a few other ways of doing this, but I think this is probably the best way. I just don't want to get into a weird situation where we have to simplify a lot to get a nicer looking answer. Maybe we can just approximate from here if you like, but I really want to strive for exactness. So, I don't know, I'm kind of in a tough spot because it's going to get a little weird, but I think we're okay maybe. I guess we would have to rationalize. I don't want to do that though. Well, let me just say this. If we had another 500 here, this is kind of like rationalizing. We'll have 3 500s in the denominator, so when you cube root that, you just get 500 out. So I multiplied by another 500 over 500, which is just 1. So we get a 500 in the numerator. And in fact, I guess we could do the same thing in the denominator by pi to get rid of this one. So just by 1 more, and then we would have a nice cancellation. Maybe we can actually do that to see what happens. So basically what happens here is that this pi will cancel with these 3 inside the cube root, because if it's a cube root of pi cubed, it comes out as 1 pi. But now we have pi in the denominator inside the cube root now. And this will come out as 1 500 in the denominator, because the cube root of 500 cubed is just 500. And this is good because 500 goes into 1,000 twice. So what we're left with is 2 times the cube root of 500 over pi. But I think 500 you can write as 1000 over 2. So this is the cube root of 1000 over 2 pi. And the reason why I'm doing that is because the cube root of 1000 is just 10. So this is 20 over the cube root of 2 pi. Now there are a lot of different ways of writing this, and if you want to rationalize from here, you can even do that as well. I don't know if it's worth it to do that. I think I'm just going to stop here, really. Really, we should just be approximating this. And I'm not going to show it, but I'll just kind of say it after we approximate. It should be the case that if you find the diameter, which is double this, it should actually be equal to this. And you can kind of see that maybe. I mean, it looks kind of like it because we got something very similar. If I notice, we just end up getting cube root of 500 over pi, but there was a 2 here. So notice if we double this, we would indeed get that. So maybe it would have been better to leave it like that. Cube root of 500 over pi with a 2 on the outside. So the height would be double the radius, meaning the diameter is equal to the radius. But again, let me just approximate this and see what we get. So I got about 10.84 centimeters for the height. And if you approximate the radius, you'll get exactly half of this, about 5.42. So that means the diameter and height have to be about the same. So let me just say for our answer, it is about 10.4 centimeters by 10.4 centimeters. 10.84 centimeters by 10.84 centimeters. Where these are each the diameter and height respectively. So I'm going to write diameter here and height here. So I hope that comes out on the screen. Let me see right now. Okay. Yeah, it seems to come out okay. All right, so this one took a little bit of time. Again, this one was a little more challenging than the previous one. There's just a lot going on, but you see the process is really the same. We drew a picture to get an idea of what the formula would be and label things accordingly, so that was step 1. Step 2 was figuring out the construction of the function in terms of one variable, which really started here, but it involved all of this as well, actually. And then step 3 was really here, where we found the first derivative and set it either equal to 0 or undefined, but again, we found out, much like I was saying, really you're just setting it equal to 0. And there's not really too much guesswork. You're usually only going to get one answer, and that will have to represent the max or min, which we're trying to find. And yeah, that was all of this. And then finally here, step 4 is interpreting. Because notice, step 3 ended when we found our answer, which was right about here, but I just took a little bit of time in actually finessing this to get a form I kind of liked. Which really probably should have stopped here, but now I'm kind of digressing. So now we're going to move on and do a few more examples. Right, so for this example, we're given a particular object. In this case, it's what is called a Norman window. So it's constructed from a semicircle and a rectangle of the same diameter of the semicircle that sits completely above it. And it has a perimeter, in this case, of 30 feet. We want to find the dimensions of the greatest possible amount of light being emitted. So find dimensions of the window so that the greatest possible of light is emitted. So basically they're asking us to maximize the area. So we understand what is asked of us now, but how do we label things accordingly? Well, the rectangle part, we can label the height as h, and maybe we can, you would probably want to label this as like base or length or something like that, but in reality, this is the diameter, which is 2 times r. So if we think of the top having radius r, because it's a semicircle, then that means the width of the rectangle would be the same as the diameter, which is 2r. And in fact, this distance around is half of that of a circle. So what is the distance around a circle is 2 pi r. Let me just shift this over so it looks a little better. There we go. So that means this is going to be just pi r, because it's half the circumference of a full circle, which is 2 pi r. So that, I think, makes a lot of sense. And in fact, now we kind of have something to go off on. We actually know that 30 is equal to that. And we're trying to maximize area. So let me just say that here we're being asked to maximize area. So this tells us to find the function for area. So area of what equals what. So remember, it should be in terms of one variable, which is why I always write those parentheses. And We also have this equation that relates to the circumference to 30, which will relate r to h. And then we can find it in terms of only one variable, because as of right now, if we were to write the area of this, it would be in terms of two variables, h and r. In fact, maybe we can just start doing that. So the area of the rectangle is going to be 2r times h, and plus the area of the semicircle will be half of the area of a circle, so half of pi r squared. And we actually have this 30 feet, which is the total perimeter again. So it's going to be 30 is equal to the half circumference pi r plus two of these h's, because we have another h here if we want to go all the way around, let's say. So 2h plus 2r. That's kind of an interesting formula. In fact, we want to solve for, I guess we can solve for h in terms of r. That's not too hard to do. Notice, actually, if you just subtract these to the other side and then divide by 2, most of these numbers are actually divisible by 2 except for this one. So you'll end up getting 30 minus 2r minus pi r, there we go, equals 2h. And then dividing by 2 gives you h is equal to 15 minus r minus 1/2 pi r. Perfect. So now we can use this to replace h with something in terms of r. It's looking kind of ugly, but now we can see that a is going to be completely in terms of r now. So a of r, it's not clear at this point though because it's in terms of r and h. But now we have this relationship in mind. So now we know that this is 2r times h, which is 15 minus r minus 1/2 pi r plus 1/2 pi r squared. Now again, this looks a little weird, but as it turns out, this isn't too bad. Because these are only r, terms in r. When you distribute, you get r squared, and that's an r squared. This one will be r though. So I'm going to bring this back in. And what's really funny is we could have just left it as 2h because 2h was here and here. But we didn't really know, well, I didn't think too far ahead with this anyways. But if you did, you would have seen that pretty clearly. So we get 30r minus 2r squared minus 1/2 times 2 cancels, so you just get pi r squared plus 1/2 pi r squared. So in fact, really this is 30r plus something times r squared. Now what that something is, really is going to be a negative value, not a positive. Because this would be -2 from this term. And then these two are -1 pi and positive 1/2 pi. Those combine to -1/2 pi. So we'll write -1/2 pi like this. But if you want to pull the negative out just to make things look a little nicer, I definitely am going to do that. There we go. Great, so now we have a in terms of r. So this was the second step of the process, which remember is the hardest one. And now the third step is just find derivatives, set it equal to 0. This is a polynomial, so it's never undefined, and neither will its derivative be by power rule, because it's also a polynomial. So it's going to be 30 minus 2 times this, which will be 4 plus pi, because we're just doubling each of them basically by distribution, times r. We want that to be equal to 0 to find the max or min. And again, this is clearly going to be a max. If you take the derivative again, that goes to 0, and that goes away, so you get a negative value. In fact, if you look at the original function, this is really just a quadratic in r, and a leading coefficient in front of r squared, leading coefficient, would be negative. So in fact, it's a facing down parabola, which has only a maximum, which I said will kind of always happen. Not the parabola part, but the always max or only minimum part, just based on the way these problems work out, as it turns out. All right, so if we add this to the other side, we get 30 is equal to 4 plus pi times r. And then dividing just gives us r is equal to 30 over pi plus 4. Or 4 plus pi, but I wrote it the other way around, which is fine. And this is going to have to be measured in feet because the only unit was feet. When we want to find the dimensions, this is just the radius. So I think the dimensions of this should be written as height times height by width. It just depends on what you want the dimensions to be. If you wanted to find the full height, that's kind of interesting actually, because notice the full height here would actually be h plus r. So maybe you can define the dimensions of this shape to be the full height from the top of the semicircle to the bottom of the rectangle, and then the width of the rectangle, which is equal to the diameter of the semicircle. But in fact, if you only found the dimensions of the rectangle, that would imply what the radius of the circle would be. But still, I kind of like this one, the complete height and complete width. That's what I'm going to define dimensions to be. Again, that's my interpretation. All right, so what are we going to do then? Well, we're going to double this, so it's going to be 60 over this, and then we're going to add it to not pi, but we're going to add it to h because of the h plus r thing, but then we need to actually find out what h is. So we can plug this r into that. At this point, we're just going to approximate because these numbers, again, this is a practical problem where you want to do measuring. So for that reason, I'm just going to approximate if you don't mind. If you want to plug it back in and see what you get, you can do that, but I'm not going to do that. I'm just going to approximate here. So let's see what we get. All right, so when you approximate this value, you get about 4.2 feet. Remember, it's in feet. And when you plug this into r and the h expression, coincidentally, we get the same kind of thing going. So it's pretty similar to the can problem where the diameter was equal to the height, actually. So here the height is equal to the radius. So with that being said, h plus r is just going to be the height plus the radius, which is the same. And then double the radius would also be the same. So the way to define this dimension as being the complete height by the diameter, the dimensions are going to be double each of these. So it's going to be 8.4 feet by 8.4 feet. Again, where one of them is the diameter of the top semicircle, and the other one is the complete height. So let me just write that as total height. Again, just to be kind of specific. And there we go. All right, so I feel we deserve to see at least one more problem, so let's take a look at least one more example right now. All right, so for this problem, we're given that a man launches his boat and rows to the opposite side of a river. He can row 6 kilometers per hour and run 8 kilometers per hour. And we're asked to find what combination of rowing and running must be done to get 8 kilometers down the river on the opposite side of the initial launch as fast as possible. And the river is given to be 3 kilometers wide. Now let me just say, this is going to be the last problem we're going to be doing in 4.7 actually. And I was debating whether we should do another geometry problem, but basically every problem we did earlier was geometry. So instead, I think that should be enough. So given any geometry type problem involving optimization, I think you should be able to do it given the previous problems, because they're all really something kind of like what we saw there. Now for this problem, this is more of we're given speed, we're given length, we're asked to minimize time actually, because we want as fast as possible. So let me just say that we want to minimize time. So that's a type of optimization we'll be doing is minimization, and the variable we're minimizing is time. And what we're going to be using is the DRT formula, distance is equal to rate times time, or if you like, speed is equal to distance divided by time. We'll be using that. The other thing that we kind of need here is to have the understanding that he is rowing to the opposite side. Doesn't say where he's rowing to the opposite side. In fact, it's very possible that you can just do a straight shot to the opposite side and do 0 running, and that may be actually faster than landing somewhere in between and then running. But we're going to assume that this is where he lands, somewhere here, and then here to here is where he actually starts running. So imagine you see him from above running or something like that. Okay, so we can call this point X so that he actually lands X kilometers away from where he started on the opposite side. We actually get here is this nice right triangle. So we have the understanding the distance is equal to rate times time. We know the rates of the boat and running. We know the distances that he is rowing and running. Rowing would be a diagonal, so we actually need to use Pythagorean theorem here. And I think we'll be okay. So we can develop some type of formula for time, and then we'll find the minimum time by taking derivative. So we need to find time in terms of something else. It's probably going to be in terms of distances, because we have a variable on the distance here, x in this case. The rates are constant, so the rate at which he rows and the rate at which he runs is constant. So I think we're okay, but notice since he lands x kilometers away, then he's going to have to run a difference of 8 and x kilometers. So whatever that distance is. So for example, let's say he rows 3 kilometers, not 3 kilometers, but 3 kilometers down like this, then this distance would have to be a minus b, which is 5, and that would just complete the 8. So I think this setup makes sense, but now given this, then the total amount of distance, so let's kind of see it like this, the total amount of distance that he would travel is given by this red line and that red line. So we have this rectangle, not rectangle, but this triangle that is an x by 3, and the hypotenuse is unknown. But notice by Pythagorean theorem, this is just the square root of 3 squared plus x squared. Perfect. So that's the distance we're traveling here. So this is the boat distance. So his distance, let's call it d, is equal to the square root of 9 plus x squared plus a minus x. Awesome. So we have distance in terms of x. Great. That's the total distance, because this is, again, the rowing distance and the running distance. So we have distance, but now, well, let's see, we have their speeds as well, but speed's going to be, it's almost like we have 2 different DRT formulas, because we have the rowing distance and rowing speed to get the rowing time, and then running speed and running distance to get the running time. So maybe we have to split this up actually. That's kind of unfortunate, but let's, at least we have an idea as far as what these distances are. But now let's see, so this actually splits because there's 2 types of distances. There's the running distance and then there's the rowing distance. So the running distance is going to be the rate at which he runs, which is 8 kilometers per hour, times the time it takes him to run, plus his speed for rowing, which is 6 times the time it takes him to row. So there we go. But we want to find the total amount of time. So this is getting more complicated. We want to find the total amount of time it takes him. So we have to solve for the sum of these two somehow. And it doesn't seem like you can actually solve for the sum of them here just as is. There may be a way to do that, but instead it seems like we have to solve for these individually. So let's first consider the running. So if he runs, then his distance of running, which is a minus x, is equal to the speed at which he runs, which is 8 times his time. So we can actually solve for time here. So his running time, so t run, would be just equal to a minus x all over 8, which actually simplifies if you split this up as 8 over 8, which is 1, minus x over 8. So that's the running time. So I'm going to circle this. Now for rowing, so his rowing distance, So his rowing distance, which is radical 9 plus x squared, I just wanted to make sure I had everything correct here. So sorry for that slight pause. Equals his rowing speed, which is 6, multiplied by the time it takes him to row. So that means the time at which it takes him to row is just that divided by 6. So the square root of 9 plus x all over 6. Perfect. So now we have the total time then, so let's call that t. So let me just emphasize that this is our total time now of running and rowing, which is just these two added together. So it's 1 minus x over 8, which is our running time, plus the square root of 9 plus x squared all over 6, and that is our rowing time. Whew, nice. So this is all step 2. Like I've been saying, the hardest part of the problem, finding the function. Some problems have the function given to you, but mostly they won't. So I'm just kind of keeping that in mind. All right, so now what do we need to do? Now we need to find the derivative of this thing, set it equal to 0. Notice, I don't think, actually it is possible that the denominator would be 0, but we're going to see that'll be a kind of weird case that you wouldn't want to consider anyways. But in any event, let me erase this so I have room for that. But of course, I kind of didn't really label the previous example correctly. I just wrote the third step, I think. Maybe I did write it out. I forget now, I'll have to go back and check. But anyways, here this is the first step and having this figured out with our labeling. And then here, once we started dealing with the formulas, this is where step 2 began and this is where step 2 ended. Because now we have a function time in terms of x now. So this is actually, we write this as a time in terms of x function. And now we'll be using this to find the derivative. So let me erase this and write that right now. All right, so I've erased things and I have the function we just got. And I even wrote it in a nicer way here so we can apply the derivative rules a little faster. So now finally we have t prime of x is equal to 1 goes to 0, negative 1/8 x goes to negative 1/8. The derivative of 1/6 times this to the 1/2 is 1/2 times 1/6, which is 1/12. That base 9 plus x squared to the 1/2 minus 1 is negative 1/2. And then my chain rule derivative of the inside is 2x. Notice we have these cancellation here, 2 and 12. Like that. And now we want to see whether this is either 0 or undefined. It would only be undefined where the denominator is equal to 0. Notice the negative 1/2 here implies that we have this in the denominator. But 9 plus x squared is never 0 because it's a square plus a number, which we've seen before. So what this tells me is that actually it's never undefined. So we're only seeing when the derivative is equal to 0. So what I'm going to do is I'm going to set this equal to 0. And I'm going to add 1/8 to the other side and write this as a fraction. So notice what we have left over would be x over 6 radical 9 plus x squared as a fraction, just like that, equals 1/8. If you cross multiply, since this is not 0, you can do that. We get 8x is equal to 6 times the square root of 9 plus x squared. This is turning out to be a little bit of a difficult problem as far as the solving part goes. The solving part usually isn't too bad, but this is a little tricky. We basically have to square both sides. We could divide both sides by 2, so we get 4 and 3. I hope that wasn't too bad that I did that. So when we square both sides, so I'm just going to write to the 2, I guess, if you understand that. 4x squared all squared is 16x squared. And then squaring this, well, 9 is 3 squared, so that'll be 9. But then squaring the radical just gets rid of the radical and gives us 9 plus x squared. Now when you apply this technique for solving these types of radical equations, you have to be careful because you may get an extraneous solution out at the end. In this case, we'll see shortly what happens. But if we distribute, we get 16x squared is equal to 81 plus 9x squared. If you subtract the 9x squared to the other side, let me just write that, I guess. Minus 9x squared minus 9x squared. What we end up getting is 7x squared is equal to 81. So all we need to do now is divide by 7, so x squared is equal to 81 over 7. And then square root to get x is equal to the square root of 81, which is 9 over radical 7. Now, when you square root, you get plus or minus, and that's where the extraneous part kind of comes from. The only thing, though, is that it's not too bad because, of course, x is a positive distance, so it's never negative anyways. So this is actually the distance that we have to row down. So now to interpret the answer here, we need to find out the distance we're actually rowing and the distance we're running. So the distance we're running is 8 minus x. The distance we're rowing was actually given by this radical part because remember it was the square root of x squared plus 3 squared. So that's x squared plus 9. And if you plug this value of x into this, we'll get something nice. So I'm going to erase this for space so we can actually interpret now. But remember, this was step 3 in finding the minimum in this case. You know, I didn't even show that it was a minimum, but again, there's nothing else it really can be. If you were to actually graph this, you'll see that this only has a minimum. But if you wanted to check, I guess what we can do is again find the second derivative for the second derivative test. Notice that would go to 0, and then we get a negative. So that means that this would always be, let me think, would always be concave down. But if it's always concave down, this is a maximum, not a minimum. So something doesn't sound right. But you know what? I'm saying that, so I'm thinking this will only come down, but we have this x in front to worry about. So that should balance things out with the product rule. But again, I'll let you kind of verify that on your own, that you'll indeed see that, well actually, for this particular value we got, if you plug this into the second derivative, it should be positive, meaning it's concave up at that point, and we actually have a minimum that we're at, not a maximum. But again, allow you to kind of see that on your own. I'm going to erase this now, and finally we'll interpret our answer by plugging things back in. Alright, so I've set some things up. This is the value we got for x, 9 over radical 7, that should say, my mistake. We're rowing this distance, radical 9 plus x squared, which again we've kind of said a few times. And we're running this distance, a minus x. So now plugging things in, notice that when you square this, square 9 over radical 7, you get 81 over 7. So this is radical 9 plus 81 over 7. If you write 9 as 9 over 1 and multiply top and bottom by 7, you get 63 over 7. So when you add those, well, you'll get, let's see, so 63 plus 81 is, honestly, there's a better way of writing this, but I guess it's 144. That's actually really nice, because since it's 144, let me see, it's 7 plus 9 is 16, yeah, that works out. So since it's 144, this is 144 over 7 inside the radical. And if you square root top and bottom individually, you get 12 over radical 7. And we can approximate this if you want, but I'll do that after. Let me just find this one now. So of course this is going to be pretty easy because this is 8 minus 9 radical 7. And I guess you can write this as 1 fraction of a radical 7 as well. But it's kind of dumb. It's just going to be 8 radical 7 minus 9 over radical 7. But regardless, let me approximate these to see if we can actually figure out what the distances are. Let me just make sure I have things written correctly. So it says, what combination of rowing or running must be done to minimize time? So we want to figure out how much distance he'll be rowing, how much distance he'll be running. Or we can interpret that to be how long he will be rowing or running for. But I'm interpreting it as distance. So that's my interpretation of the way it's worded. So let me use my calculator now to approximate these. Alright, so I used my calculator and I got about 4.5 kilometers of rowing and 4.6 kilometers of running. Awesome. Now, again, that was my interpretation of what the question is actually asking us for, because when it says what combination of, it doesn't say what distance must he row or run, but I'm interpreting that as distance. So let me just write it as row 4.54 kilometers and comma run 4.6 kilometers, which is actually about the same. So for whatever reason, we're doing the same amount of rowing and running. And in fact, I find it kind of a little weird that that he runs faster than he rows, but it could be that he's going against the stream, or maybe he just doesn't row that fast. But maybe it's just me, but I would imagine that you would row faster than you run. Maybe it's not the case though. I actually haven't done that much rowing in my life. So anyways, so I'm speaking from limited experience. Maybe you can tell me what you think as far as that goes. But that's it for 4.7. That's all I wanted to say anyways. I hope I gave a good variety of problems here, because honestly, optimization problems, they're all basically word problems and they're kind of different to some extent, but usually they're geometric. So I gave mostly geometric problems. This is kind of geometric because we had a Pythagorean theorem going on, but it was more physical than anything because it involved distance equals rate times time, which is a consequence of physics, kind of. Anyways, hope you enjoyed this. I'll see you in the next video for 4.8, where we'll be discussing Newton's method, which is kind of a take on linear approximation from chapter 3. It's a little weird if you think about it. This is the chapter 4 version of 3.9, which is related rates. The related rates and optimization are kind of different, of course, but there's still word problem applications of derivatives, kind of. And Newton's method is kind of similar to 3.10. So 4.8 will be similar to 4.10 in the sense that it's a technique that involves derivatives that allow you to approximate certain values. It's actually a whole lot of really good material, and I want to say that it's going to be pretty fun, but it's more interesting than anything, because we'll actually see how you can evaluate certain values by hand using calculus without the need of calculators. We'll still be using our calculators kind of for approximations like we did here, but I'm going to try my best not to use certain operations like square rooting and stuff like that, mainly Newton's method only requires multiplication, division, maybe some powers. But things that you can certainly do by hand if you wanted to, but we're just not going to be using things by hand too much because the calculations become a little tedious. Anyways, I think I spoke enough of that. We'll actually see more of that in the next video. So thanks for watching this, and I'll see you then.